Next speaker, our next speaker is Benny Pinkas. There are many Bennys in Israel, and so Benny is a professor of computer science at Bar-Ilan University, and before Bar-Ilan, he had spent quite a bit of time in the industry, and as a result, I don't know if as a result of that. But he's extremely passionate about transforming the theory of MPC to practice. He had been in the forefront of making MPC practical. He's been really pushing the frontier of practical MPC. And today we will be hearing similar stuff from him. So the talk is specifically one particular application of MPC, namely private set intersection, PSI. So he will be talking about that. Okay, so.
Okay. Hi everyone. So this talk is going to it's going to be different than the set of the previous three talks. It's going to talk about a problem I worked on a lot in recent years, which is private set intersection and private set intersection analytics. And it's about doing MPC beyond the generic computation that uses circuits to compute MPC. So I'll start with some, high-level view of MPC, then I'll go into the details of set intersection and some recent developments from this year or last year. And this is joint work with many co-authors, including mostly Thomas Schneider from Darmstadt and Avishai and I from Bar-Ilan and Mike Wasulek and their students. So I wasn't here on the first day of the workshop, but MPC started with the seminal work of Yao, who looked at this millionaires problem, which is a toy problem. If I want to introduce MPC to someone, I describe this problem: the two millionaires, X and Y, Alice and Bob. And they want to find out who has more money than the other. And they want to do it without leaking any other information. So they should learn just one bit of output. So if they had access to a trusted party, say to Apita, then each is going to whisper in her ear, how much money he or she has. And Apita will give, one bit of output. But suppose you don't trust anyone and you want to do this without a trusted party. So in that case, we noticed that standard crypto tools like encryption or signatures don't help us. Encryption is used to secure the communication between them from any auxiliary outsider who tries to eavesdrop. But here we talk about the actual people in the room who should not be, who do the computation, who should not be able to, learn anything. So if we look at it at a high level, all of the traditional crypto, classic crypto, up to here, was about taking things that we can do securely in the physical world. Like if I want to tell you something, tell someone here something in secret so others will not hear it, I can whisper this thing in that person's ear and we know that no one will be able to listen. If I want you to be sure that I'm saying something, you see me, you know that I'm saying this. And what is classic crypto, like encryption and signatures, is taking these things that are clear in the physical world and trying to implement them when you communicate from far away, over the internet, over the radio, or whatever, or with, when you send couriers in the past. Here, it might be the first crypto task that we don't even know how to implement in the physical world. So it's not clear how, these two can do it. So it seems much harder than the classic crypto tasks. And Yao, he showed how to solve it. Now, in terms of security, what we want to gain in MPC, and I'm sure you heard it, is the same security as if you had a trusted third party. So obviously, the trusted third party, we assume it's secure and doesn't leak any information. So obviously what you learn here from the trusted third party, they learn the output. And the goal is not to learn anything more than the single output bit. Now, MPC started as a curious mental game, like what Yao, this game that Yao examined. And in the early days, they did fun work with, papers like the millionaires problem, poker over the phone. They looked at it as mental challenges. And MPC research for many years has been theoretical. And since maybe 98, we started working on actually implementing it, and we realized that I think these theoretical feasibility results can actually be implemented in practice and can be efficient. And we worked a lot on trying to make it more and more efficient. So this is something which might not be required for this audience. Like basic research is important. It seems like mental games and just we let scientists play, but sometimes some important things come out of it. So even this millionaires problem, which is a game, it has applications. So if we talk about trading stocks, if you want to trade stocks, say Alice and Bob, then Alice wants to maybe sell some stocks, and the minimum price is this, and Bob wants to buy some stocks, and his maximum price is that. And what they want to do when they trade stocks, they want to find out, if the Alice ask price is larger than Bob bid price, in that case, there's no deal. And if so, there is deal, and the amount of trade that they should do is the minimum between how many stocks Alice and Bob want to trade. So even this game of Yao is actually very relevant to stock trading and for auctions and bidding, and can be very useful in practice. Now, when we define security, we want them to learn the output and nothing else, as if they had a trusted party. So we cannot hope for more privacy. And what we should do is first, not as researchers who want to examine these things, but someone who wants to deploy MPC. So here maybe I'm talking to executives. First, we should think whether the trusted party makes sense. Are the parties motivated to submit the true inputs? So it might be that Alice wants to show that she has more money than Bob. She'll input 10 to the power of $40 as how much money that she has, and obviously she will win. So in that case, there's no use in running the game. Also, we should check if the parties are happy with the disclosure of the output, whether learning the output makes sense. Sometimes the disclosure of the output is too hard. And these are things that you can examine even without thinking of MPC. If you had a trusted party, these are things that you want to examine. And if they don't hold, then you don't even use a trusted party, because the parties are not up to computing this. What we do in MPC is, if these conditions are met, what we can do is get rid of the trusted party. So all that MPC is doing is letting you do a computation without relying on a trusted party. So we take a computation with a trusted party, and we do it without it, with some levels of communication. So saying it again, MPC doesn't tell you which function is safe to compute. You have to decide on it by yourself, imagining a trusted party. It only shows you how to compute this function without a trusted party. So this is like a meta discussion. And it took a while to understand this. Like when I doing my PhD, and I gave talks, and people gave me hard questions. I didn't know how to answer them, and the questions were about whether this function makes sense to compute. Not about whether the computation makes sense, because sometimes if you do auctions or things like this, the settings where MPC doesn't make sense, but trusted party also doesn't make sense. Okay, so how about implementing secure computation? I won't tell you how to do it, but Yao showed how to do it back in the 80s. And what she showed, not just how to compute the millionaires problem, but how to compute any function. And this design of his was considered theoretical until we actually started implementing it, and then worked a lot on making it more and more efficient. And the thing to remember is that this computation is based on the first step of expressing the function as a Boolean circuit, or maybe an arithmetic circuit. So that's the first step, which as theoretical computer science, it makes sense. Any function that runs in polynomial time has a polynomial size circuit, so it's efficient. The question is whether it makes sense in practice. And then in recent years, a lot of very smart optimizations came into this. And the performance depends on the circuit size and many other factors, like the setting, how many parties you have, what kind of things they can do, security requirements, whether you can invest in pre-processing, then everything else can be much more efficient. And a lot about engineering and using the most recent and fastest architecture. And if we look at maybe state-of-the-art computation of AES, So suppose Alice has the key and Bob has the input, and they want to compute the encryption of Bob's input with Alice's key, and only Bob learns it. So this is kind of a test case. So state-of-the-art solutions, the runtime go between 1 microsecond and 1 second per block. I'm not very accurate, but they're like 6 orders of magnitude in the difference in the latency, or more in the bandwidth. Not the latency. And it depends a lot on these parameters. So there's a lot of play there. And these days, in terms of size of circuits, we can definitely handle circuits of millions or even billions of gates, but not much more than that. Okay. And this talk is about going beyond this generic computation. So far, everything seems good. Efficient circuit gives you an efficient MPC protocol. A function with polynomial runtime gives you a circuit of polynomial runtime. So from these 2 points, we know that if we can efficiently compute a function, then we can also run an MPC computing it efficiently. So theoretical computer scientists who think about feasibility are happy at this point, okay? But if you tell this to someone who actually has to implement it, then they can start, they think that you're laughing at them because they haven't, unless they work on VLSI design, they haven't implemented a circuit, they thought about circuits since the first year in undergrad, and they don't know, how you design a circuit for implementing a function. And the overhead depends on the size of the circuit, and you tell them it's, you do a reduction of your algorithm to a, to a large formula, and then, implement a circuit computing it, they'll start laughing at you. Okay. So let's look at examples. So suppose the 2 parties have integers x and y, and they want to compute the sum of these 2 integers, okay? So here we can go back to elementary school, and we know how to add 2 numbers. We start from the least significant bit, add the 2, least significant digits, move a carry to the next digit, and so on. So we usually do it in base 10 in elementary school, but we also do it in binary. And the number of gates of that circuit is linear in the length of the inputs, which is very efficient. That's great. So that's efficient. What about subtraction? So subtraction is just like addition, or you can move one number to 2's complement, so it's also very efficient. What about comparing 2 numbers? So comparing is basically subtracting them and checking if there's an overflow. So it's also efficient. What about choosing the maximum? So we compare them, and based off that, we choose one of the 2 numbers, do an end of the result to the 2 numbers with some changes. It's also efficient. So this is great. These operations are great. What about multiplication? So again, we go to elementary school, like, we multiply 2 numbers, we write them, multiply the least significant digit and the next one. So multiplying 2 n-bit numbers is like n additions, so the overhead becomes quadratic in the length, which is less fun, but still doable. And exponentiation is like doing n multiplication, so the overhead is quadratic, but raised to the power 3, but still it's cubic, but it's still doable. Okay. All right. Suppose we want to do other things, so arithmetic, like comparing stock prices. It seems doable. What about other things? Now, suppose that x and y are 2 sets of data, and we want to compute the intersection. So here the naive solution would be to compare each item of x with each item of y. So the number of comparison will be quadratic, which is too much if we have, let's say, 1 million items per item, per set. And computing the median also, it's not, or other statistics, it's also not clear how to do it. And perhaps the most inefficient thing is doing associative accesses to memory, like looking at the memory at a location which is secret. So we want to look at x, which is an array, at index y, where y is secret. So if we implement this using a circuit, we have to basically read all items of x and choose just one of them. So each time we want to access one item, we have to read the entire memory, which of course it's not reasonable. So if we sum up, this arithmetic is rather easy. Accessing memory at secret locations is very not easy, and you do this with ORAM. And I'm going to focus on this, on doing operations on sets, and try to do it more efficiently. So let me talk about using specific versus generic protocols. So sometimes we have a specific problem which is very important, and for that we would like to design a specific protocol which is very efficient for that problem. Usually it's not the preferable option. The preferable option is to use like a generic tool that is good for solving all problems. Because if we do something specific, we might have errors. We have to design a lot of person years or months, which are very expensive. Maybe we cannot compose it with other things. And if we have a generic solution, we can invest a lot in optimizing it and just using it. So it's not good that here we cannot use generic solutions to say compute the intersection. This is what I'm going to talk about today. So let's get to the private set intersection problem and its variants. So the basic problem is when we have two parties, Alice and Bob. They have sets of inputs, and they want to compute the intersection without leaking anything else. So suppose that both of them, or just one of them, has to learn the intersection of the two sets without learning anything else. So you can think, suppose we have two teachers at university. Each teacher thinks that some students are cheating, but they're not sure. So let's think, okay, if both of us suspect the same student, then we should maybe call that student. But otherwise, I don't want to leak to you what I think. So they want to compute the intersection and not leak anything else. But the sets will be much larger than hopefully the number of students you have in your classes, or my class, yeah. Although I like to have a lot of students, but not millions of them. Okay. So apparently private set intersection, PSI, has a lot of applications. So it's good for information sharing. Say intersection of threat information. So threat could be students that are cheating, or maybe companies see all kinds of suspicious behavior on the networks. And I want to see if what happens on my network, also other companies are seeing it, but I don't want to leak to them what happens on my network. It's good for matching, for testing compatibility. So suppose two people want to date, and I have a list of a lot of sentences that represent me, or movies that I like, and the other person also has a lot of such things, and we want to check for compatibility without leaking that I like cartoons or whatever. It also can be used for genomic compatibility. And for something important here is that if we suppose we want to compare the first item in my set to the first item in the other person's set, and the set might be my preferences or my genome, then the problem is easy. My first item is compared to their first item. My second item is compared to their second item, and so on. So if you have n items, it's n comparisons. So that's easy. The hard problem is when my first item can be, in theory, equal to any of the n items of the other party. Okay? So then the number of comparisons, the naive one, is n squared. This is where we want to save. So if you just compare the items like index by index, that's easy. The question is what happens when the comparisons are kind of free. This is a matching. Join, if we do database operations of join, basically we compute the intersection and things on top of the intersection. Analytics, so if we do big data analytics, we want to compute what's the probability of A happening given that B happened. What's the probability that I'll be buying beer if it's known that I bought diapers, something like this. So this probability basically count the the intersection of things in both A and B and divide it by this probability. So you have to count the intersection. And if these sets belong to different parties, we need to somehow compute this without this number, actually, not the intersection, but this number without doing something else. And here are two applications I'll talk more about. So one is identifying mutual contacts. Okay, so suppose Alice has she installed an app. This is relevant for the Signal messaging app. And the app wants to have access to Alice's contact list, because the app wants to find who on the app's database is also using Alice. Sorry, who of Alice's contacts is also using the app. If it's a messaging app, it's obviously needed because Alice needs to contact her, to talk with her contacts. If it's another app, perhaps they want to give me an experience which is based on what my friends do on the app. because this might, a good prediction to what I like. So they would like to know who of my friends are already using the app. But if you care about privacy, you don't want to upload all of Alice's contacts to the app database. You just want to compute the intersection without linking anything else. So and actually the Signal messaging app are using a variant of private site intersection to do this, although they use SGX for that purpose, not a cryptographic protocol. It's, with their scale, they claim that they cannot use MPC for that purpose. Okay, so to be more concrete, we will look at the following definition. We have two parties, Alice and Bob. Alice has a set of X of items, Bob has Y of N items. And suppose that Bob needs to learn the intersection of the two sets. Battery died. Okay. We can also think about the battery died, but that's okay. You can also do it like this. Okay. In addition to looking at computing the intersection, we can also think about doing analytics on top of the intersection. So in that case, we don't want Bob to learn the intersection itself, but some function of the intersection. Okay, so for instance, a simple function is to Bob to learn how many items are at the intersection rather than exactly the names of the people who are in the intersection. Another option is if we associate each item with a payload, okay, and the function should be based on the items in the intersection and the payload, okay? So I don't know who is in the intersection, I don't know what's their payload, but I learned some function of that. And I'll give you an example. So this is an example that Google published on how they use private site intersection. Actually, they do analytics based on the intersection. They don't learn the intersection itself, but some function of it. Okay. So here's the intersection. So, we use Google. I use Google, so I register. They know who I am when I know whatever I do on the web. They show me ads. Suppose they show me an ad for an ice cream. I go to sleep. I dream about the ice cream. This is Abishai, a nice slide. And then the next morning, I go and I buy the ice cream offline. Okay? So Google would somehow like to, notice the fact that I bought ice cream because of the ad, because then they can go to the advertiser and tell the advertiser, look, you gave us the ad, and you made money because of that. And that's not funny. This is, thank you. This is how Google is making, their money. So that's, this is what they do. And to make more money from ads, you have to show advertisers how much they made from it, and then you can charge based on that. And if the purchases are done online, then you can count how many clicks were. But if the purchase is done offline, you need to connect this. So one simple thing is for this merchant here to send to Google the information of everything who bought ice cream. Suppose this is done with a credit card. Or suppose it's not an ice cream, it's something bigger. Okay. But if the merchant cares about privacy, then basically here we have a list of people who did transactions and an ID, which is a credit card. And Google has the names of all the people who saw this ad and suppose their credit card or phone numbers, and they want to compute some function of that. So Google, the MasterCard, suppose I use MasterCard for this transaction. Google has some agreement with MasterCard about this based on press releases, and Google has information. And they don't want to compute who saw an ad and bought ice cream, because this might be sensitive information. They don't want to compute how much each transaction was. They want to compute the sum of transaction, how much money was made because of the ad. There may be some other function of the, of these purchases, maybe variance or something like this. Okay, so this is an example of not computing the intersection, but computing some function of the intersection. So we would like to implement this. So when you talk about implementing computing private site intersection, and you give people the time to think, then they usually come with the following idea. They say, okay, Alice, they should choose some one-way hash function, a cryptographic hash function. Alice will send to Bob a hash of each of her elements, and Bob will compute a hash of each of his elements, and he'll compare the hashes. And if there's an x of Alice which is equal to a y of Bob, the hashes will be the same. And if the output of the hash function is long enough, then there won't be any other match. So here Bob can use hash tables or maybe n-square comparisons, but this is like simple operations on plain text, and he can find the intersection. And since the hash function is one way, then given this, he cannot go back and find Alice's inputs. So this is good as long as the inputs have a lot of entropy. If the items don't have a lot of entropy, suppose these are credit card numbers, then Bob, when he gets these values, or even before that, he can compute a hash of every possible credit card number, and then just compare these values and basically do a brute force attack and learn, what inputs x correspond to these hash values. So he doesn't reverse the function h, he's just doing a brute force attack over the entire possible input domain. In all application scenarios I know, the input domain is rather small. Okay, so this is a naive solution, and at some point you read what companies are doing. It seemed that some companies, not Google, are implementing this, but this is insecure. I can't think of a setting where this is secure. Another type of solution is based on public key crypto, for example, Diffie-Hellman assumption. So this is a protocol based on Diffie-Hellman assumption. So something to notice. I'll go over the details, but ignore them for now. So the first thing to notice is the reference here to Shamir from 1980 on a paper on the commutativity of encryption. So this is an old protocol. Here it's a bit hard to find it. This is the paper of Catwing Meadows from 86. There it's definitely written. So it's an old protocol, old crypto. Another thing to notice is that it's simple to understand. I'll describe it in a minute, but a few lines, there's nothing here to understand. So let's see what happens. So Alice has a secret key alpha, Bob has a secret key beta. These are the inputs. Alice computes a hash of each of the inputs to some group where she can raise to the power of alpha, and where the discrete log is hard, or Diffie-Hellman assumption, the decisional Diffie-Hellman assumption holds, and computes a hash and raises everything to the power of alpha and sends to Bob. Bob does the same to his inputs, maps them to the group, raises to the power of beta, sends to Alice. Then he also takes the values he received from Alice and raises them to the power of beta. So he received hx1 to the power of alpha, raises it to the power of beta, it sends back to Alice. Alice takes these values, raises them to the power of alpha, and gets these values. So basically, what Alice gets here is everything she sent raised to the power of alpha and then beta, and everything that Bob had raised to the power of beta and then alpha. And since exponentiation is commutative, then if they had two equal inputs, she'll find equal outputs. So this is great. Basically, it's just like the insecure function solution we had here. The problem here with the hash function was that Bob could do a brute force search and compute it over the entire universe. Here, the hash function is essentially taking something, hashing it, raising it to the power of alpha and to the power of beta. So Bob cannot do a brute force over the entire universe of computing this function, because he cannot raise things to the power of alpha. Only Alice can do that, and she can only do it like n times. So, okay, it's easy to show this is secure in the semi-honest scenario. It's simple to understand. If you haven't understood it, another 3 minutes and you can understand it. Seems very simple to implement. It can be based on elliptic curve crypto, and therefore the communication is very small here. The problem is that you have to do a lot of computation, a lot of exponentiation. So maybe you can do 1,000 of this per second, but it's not very fast. Unless you use someone like Google, and you can put a lot of machines, and you care more about communication than computation. So there were more efficient constructions. This was not in the year one. It was maybe 15 or 14. And basically, what we noticed there was that we can reduce private side intersection to oblivious transfer. And since we had oblivious transfer extension of Yuval, Kobe Nissim, Joe Killian, and Erez Petrank, then we can do OT extremely fast. So we just move everything to oblivious transfer, strip everything else out of the oblivious transfer, use also hashing techniques, and try to do it as fast as possible. And indeed, we managed to do it very fast. So this is the landscape of PSI up to maybe 3 years ago. And I'll show you how fast it was. So this is for specific settings. So let's go through the slides. This is the communication overhead, and this is a logarithmic scale. So we want to be as close as possible to here. This is the runtime, also logarithmic scale. So here it's like the optimal place in terms of performance. This is the naive and insecure protocol of just hashing with a one-way function. Of course, it has the best performance. And the best OT-based solution that we had was 6 times slower, which is not bad. And it became a bit better afterwards. Now, the red thing are the public key-based solutions like the elliptic curve one I showed you. The nice thing is that if you use elliptic curve and Diffie-Hellman, then the overhead is as good as this. Actually, with the OT, we had to work hard to get to the communication of the elliptic curve one. The thing which is not nice is that the runtime is like, this is logarithmic scale, maybe 100 times slower. Here are circuits which are based on solutions which are based on circuits. It's not a circuit that is doing n square comparisons. It's the n log n circuit. I'll show you in a minute how to do it. But it's pretty bad both in terms of communication and runtime. And our goal is to try and make this more efficient. Okay, one question is why look at circuits if you have these efficient protocols? And I'll give you an answer soon. But another question one might ask is, okay, what's more important? Is it more important to have good communication or good computation? Where should I optimize? So people usually say communication is more important because I can parallelize computation. But suppose there is a solution based on accumulators, which has it's Ateniese and Emiliano and I forgot the third author. So it has the best. It sends just one element. So the communication is like minimal, but you have to do n log n exponentiation. So in terms of computation, is way over there. So what's the best thing to do? What should we optimize? And then we had an answer in a recent paper with Avishai Anai and Michael Sulek and Initriu. We said, okay, money is the thing we should optimize. We said, okay, Amazon or other cloud providers charge us money based on how much these resources cost. So both communication and computation, you can translate them to how much we have to pay for that. And let's assume that how much AWS charges us is the actual worth of these things. So here we had this is how much communication we use, how much runtime we use, and these curves are points which are equal in terms of how much we have to pay for them. So here we have a lot of communication and no computation. Here, runtime and no communication, and this curve that we all have to pay the same. For each point here, we have to pay the same amount to Amazon, and we want the protocol to be as in an inner band as possible. Okay. So you see here the Diffie-Hellman based solutions. They have low communication, but they cost a lot. And this is the fastest protocol based on oblivious transfer, which has great runtime and high communication. And then this work from Crypto 2019, we managed to optimize everything and be in an inner band, like have maybe not the best communication and not the best runtime, but the overall combination of all of them seem to be optimal. So KKRT stands for Koleshnikov. Excuse me? No, it's based on OT. It's OT with OT extension and some coding, yeah. It's based on OT. Yeah, actually, okay, if I remember correctly, the paper was not accepted the first time, because I think we tried to claim that we had the base communication, and they didn't buy it because they said that, so this is ours with the best communication. So we had two versions. One is with the best overall performance. This is one where we optimize communication. So in the initial version, we wrote that this is the paper with the best communication, and then they told us, but look, there's this paper which uses accumulators, and since it's one item, so the communication is like way smaller than this. But the computation is much higher, but you cannot claim that your communication is the fastest. So then we realized we have to somehow combine the two. So, I mean, sometimes you get reviews that, make you work and get like a, better understanding. So, and then we combine the two. So I guess that the protocol with accumulators is somewhere here, and you have to pay a lot for that. And I don't know how to compare communication and computation, but I assume that Amazon are making money, so they know how much to charge. So yeah, maybe the cost is some. I'm sure that if I was running my own data center, the cost would have been different. But then I could have run this, do this for myself if I had people who know this. Okay. So what we want to do is not to compare the intersection itself. We want to do like computation on top of the result of the intersection. So what we want to do is to, not for Bob or Alice to learn the intersection, but for them to learn shares of the intersection. And then they can run any MPC protocol they like and compute whatever function they want, like some money, whatever they need to do. And if we have a solution for this, we can compute any function we want. And it's also modular. We can compose any function we want. And a nice thing about solutions of this type is that we write it once, and then we have to do, we can compute anything with it. So if we look at specific protocols for PSI, so the protocols I showed you previously on the graphs, they were used for computing the intersection itself. So suppose I compute the intersection, and then I want to sell it to a company, and they tell me, okay, we don't want the intersection, we just want to know how many items are at the intersection. So then you have to basically get a cryptographer who will design a new protocol for you. And then they come and say, actually, we don't want to learn how many items, it might reveal information, so just maybe add some noise to get differential privacy. So you have to hire the cryptographer again who will design a new protocol. And hopefully they'll be able to design a new protocol. And then they say, actually, we don't want to learn exactly how many people there are, but maybe some other thing, some statistics. So each time they make a change, we have to hire cryptographers again. Whereas if we can apply here generic secure computation, then anytime they change the specification of what we have to compute, we can hire a second-year undergrad, a smart undergrad, who did well in his, the course where they learned about Boolean circuits, and ask that person to design a circuit for us. And yeah, and that's it. So it's basically, we can start programming or doing programming for this instead of having to design and prove new protocols. So this is great. The problem is that, if you recall the graph, these protocols were way inefficient, and we tried to make them more efficient. So comparing in a circuit two numbers is very simple to check if they're equal. Basically, you XOR each of the bits, and you want to make sure that all the results of the XORs are 0. So that's very simple. The question is how to decide which items to compare. So the algorithmic challenge is to find the smallest circuit for computing the intersection. Alice and Bob can prepare the inputs, perhaps sort them or hash them, whatever, but the circuit must not depend on the data. It should be oblivious to the data. And after we have the circuit, we can compute whatever function we want. After we have a circuit for the intersection, we can compose any other function on top of it. How much time do I have? 15? Okay, 20, okay, it's okay. Okay, so how we design a circuit for computing intersection? So the naive circuit will do n-squared comparisons. But a protocol based on sorting networks can do it in n log n comparisons. I'll show you in a minute. And with OT, we managed to move this down to n log n over log n with very small constants. And now we get to linear. And today I'll show you a linear overhead of order of n, also with small constants. So just about how to do it with sorting networks. So sorting network, are you familiar with sorting network? Yeah? Even the young students, because they were designed in the 50s or 60s in the contents where they had to route phone numbers, phone calls. So basically they had a physical, so I was told, physical boxes that get two phone lines and can compare the two destinations, and they also had two outputs, and either they could send them in the same order they got or in reverse order based on the indexes that came in. So basically you had boxes that compare two numbers and you sort these two numbers. So these are the tiny boxes, and based on these boxes you can arrange them to sort an input set which is of n items. So basically you have a building block that sorts two numbers, and you build a large network from it for sorting n items. So in general, it can be done in n log n time with a very large constant overhead. A construction with n log square n is very efficient. If the question is different and we have two input sets which are already sorted, and the task is just to merge two sorted input sets, then you can do it in only n log n comparisons with a very small constant. Okay? This is called a Batcher merge network. So we can implement this using MPC. Basically, it tells us what circuit to do. In each box like this, we have to compare two numbers, and we know how to compare two numbers. And so what we do here, okay, so the two parties each prepares a sorted list of his or her inputs. We run them through an MPC which implements this sorting network with n log n comparisons, and we get a sorted list of the union of the two parties. Now, if each party had an input which contained only unique items, and we can require this, then, okay, and if the two parties both of them had the same value, say x, then in the sorted union, we'll have the two occurrences of x right next to each other, because the union is sorted. So then we have to run a linear circuit over the sorted union and just check if item number I is equal to number I plus 1. Just check all adjacent pairs of items, and then we'll identify the intersection. And then on top of it, we can compose whatever we want to compute any function, number of intersections or whatever, sum them up or whatever. And this takes n log n comparisons and small constant. Okay, and we want to do it more efficiently. So I'll describe what we do. I'll describe our recent construction, but I'll start with some background. So one tool we can use for private side intersection is oblivious pseudo-random function evaluation. So this is an MPC that solves the following problem. Alice has a value input k, not really input, but suppose she has an input k. Bob has an input y, and Bob learns a pseudo-random function keyed by k applied to y. So think about it as AES. Alice has a key k. Bob has an input y. He learns the encryption of y with the key k. So the protocol, actually the more efficient one, Alice cannot choose the key. The protocol tells her the key. But it doesn't matter because Bob will not learn the key, and all that we need from a key is for it to be random. So it's a very efficient protocol. And OPR, if it's a known protocol, it was optimized. We can implement it very efficiently. How can we use OPRF for compute the intersection? So, okay, for each of Bob's inputs, he takes his input y, inputs it to this box, and gets an encryption of y with this key k of Alice. Okay, so basically he gets an encryption of all of his inputs with the key k of Alice. Alice doesn't know what are these encryption. Then Alice sends to Bob an encryption of all of her items with that key k. And Bob is just doing these comparisons. And so if there's something in intersection, he'll find this. Okay, I was a bit confused here. Here we talk, suppose that Bob has just one item. So if he has one item, he'll get an encryption of it with the key of Alice. She'll send Bob the encryption of all of her items. He'll do this comparisons, and he'll find if his item is in intersection, in Alice's set. And since he cannot compute the function by itself, he doesn't know K, he cannot do a brute force search and find, what values, what inputs these values correspond to. So this, if Bob has one input, we can compare it to see if it's in Alice's set. Okay. Okay. Now suppose they have two sets, so they can repeat it n times. So Bob has n inputs. He will run an OPIF with each one of them. And for each one of, suppose each of these OPIFs, for the most efficient OPIF, it has to be with a different key because it can only be used once. So Alice will have to send Bob, encryptions of her inputs, and then they compare this in a circuit, and he'll get, values of whether they're equal or not, and he can do other computation with them. But there's a problem here. The problem is that each of Bob's inputs has to be compared to the n items of Alice, so we get n squared comparisons in circuit, which doesn't look good. So this is what we want to try and solve here. So what we achieve, we're going to get to the first PSI protocol with linear communication. It's if you assume the OT hybrid model and correlation robust functions for the OT extension, then that's all that we need here. If we look at concrete overhead, this is much better than, this is not a protocol we had last year in Eurocrypt, and now we get about 10 times less communication and much better runtime. This is the best, this is the Diffie-Hellman based solutions, we're much faster. And we can get payload like the money that's associated with the transaction from both parties and compute whatever we want with it. Okay, how are we going to do it? So the first thing we're going to do is use a trick that was used in PSI for some time, which is to do hashing. So suppose, okay, we have a hash function that maps items to bins. And suppose each set has n items, and each party maps his n items to n bins using a random hash function. Okay, it doesn't need to be a cryptographic one. So Alice's items go to n bins, Bob is doing the same, and they both use the same hash function age. What we see here is that if Alice and Bob have the same input, then they're both going to map the same input to the same bin because they use the same hash function for that. So now Alice doesn't have to compare this item to all of Bob's inputs, just to the items that Bob put in this bin. Okay? So instead of computing n squared to n squared, we have to compute the items that Alice put in the first bin to the items that Bob put in the first bin, and so on. So the number of comparison becomes much smaller. So on average, it's really nice. On average, they're going to put like one item in each bin, so they have to do like a constant number of comparisons for n bins. Seems like we got to linear overhead. But the problem is that Alice doesn't want to tell Bob how many items she has in each bin. Because, suppose that, hash of Yuval is 1. So if I have Yuval in my set, I'm going to put it in the first bin. And I do a PSI with someone, and I tell that someone, look, we don't need to work with the first bin because I don't have any item in the first bin. So then they know that Yuval is not in my set. And this can be generalized. So in general, the party shouldn't know how many items the other party put in that bin, in each bin. And the only way to get rid of that is to pad each bin. No, we cannot remove items from bins. So we pad each them to be as big as the largest bin. And if we map n items to n bins, then with high probability, we're going to get about log n items in the most populated bin. We can analyze this. So we're going to get like n bins. Each one of them has log n items. And comparing this log n to that log n is going to take us log n squared. So the overhead is going to be n log n squared comparisons. Maybe a bit better, but this is, and we want to do better. The next thing that we can do, it was used before, is using Cuckoo hashing. So do you know Cuckoo hashing? The people here, the undergrads here, do they learn Cuckoo hashing? They know, almost no one they learn, although they should learn it, I think, in basic algorithms courses. So, okay, so I'll tell you about Cuckoo hashing, and this might be the most useful thing you will learn from this talk. although it's not mine, it's not about cryptography. So this is about Cuckoo hashing. Okay, so in general, if you're just using a hash function, maybe not for crypto, and you map n items to n bins, you get collisions. So you're going to start maybe using linked lists in each bin. It's much nicer if you have just one item in each bin. So Cuckoo hashing due to Pa and Rodler, and this is a version from Hirsch, Mitzenmacher, and Udi Wieder. So they use two hash functions, and you mapped n items to slightly more than 2n bins. So you pay because you have to use more bins, and each bin can store at most one item. And the property is that each item is put either, item X is put either in H1 of X or H2 of X. It can be put in one of two locations. And Y can be put in either H1 of Y or H2 of Y, in one of two locations. And if you have this freedom, then with very high probability, you can put all n items here and use just one item in each bin. So then when you do the lookup, you have to look for an item in two locations, but you know that each bin is going to store just one item. So this succeeds with good probability, which is good enough for people who work in algorithms. And what was shown is that sometimes it doesn't work, although with good probability it does work. But if you have a stash where you store some more elements, so suppose the stash can store additional S elements, and if you try to put X in two locations, you cannot find place for it, not here, not there, and you start moving other items and you cannot solve this, then you put an item in the stash. So if you put S items in the stash, the probability that you're going to succeed in mapping the items if you use random hash functions is 1 over n to the power s plus 1. So suppose you have a stash with just two items that you put here if you get stuck, and n is 1,000,000. So the probability of you failing is 1 over 1,000,000 to the power of 3. So 2 to the minus 60, the probability of failing, which is great. Okay. So this is a polynomial failure probability that for all practical purposes looks great. If you want to reduce this to be negligible, then we have to work hard. But for practical purposes, it's okay. We also have a solution that shows negligible failure probability. Okay. So how do they do it? Okay, so what they do is, we had a problem when they started mapping items to bins because they had to put too many. So Bob is going to use Cuckoo hashing. So he's going to put each, they're going to use 2 plus something bins. He's going to put each item either here or here. He's going to have just one item in a bin. So X is going to put Y of Bob is going to put either in H1 of Y or H2 of Y. Okay, one of two locations. Alice is going to put each of her inputs in both locations to which it can be mapped, both in H1 of X and H2 of X. Okay? So Alice is going to end up with bins which have log n items in them, maybe 2 log n items. And Bob has bins with just 1 item in them. And we still have this stash with a few items in it. And now they need to do the comparisons. The nice thing is that we have to compare the log n or 2 log n items of Alice with just this 1 item of Bob. So we don't do log square comparisons, we do log n comparisons per bin. So the total number of comparisons is going to be n log n. So this is not new, it was known before, and our goal is to reduce it to be just 1 comparison per bin. Okay, so it's n log n, we want to make it better. And we still have this stash which is annoying, but I won't go into it. Okay. So we want to do just 1 comparison per bin. So we were using this OPRF, where Bob, say for a bin, inputs his Y, get an output, fk of Y, and then Alice should send him fk of each of the log n items she has in the bin. So instead we want to do 1 comparison. So instead of an OPF, we're going to use a new thing we call an oblivious programmable pseudo-random function. And let me describe it. So this protocol, Bob inputs Y, Alice has a key K. In addition, she inserts a set of items, inputs, and she programs the pseudo-random function so that if Bob's input is not one of these values, he's going to get a pseudo-random output. If his input is one of these values, he should get this y star that she programmed. So it's a pseudo-random function, and Alice programs it. Say for log n values, the pseudo-random function should give a specific output. If Bob evaluates the function only once, he won't know if he learned the programmed value or not, because he can see it only once. But Alice it's almost like puncturable pseudo-random function, but other way. Like for a certain number of points, you want to program it to have a certain values. And then to compare, Alice just sends this y squared to Bob, and he's doing a single comparison. So we don't need to do log n. It doesn't need to send him log n values, to send him just one value, and he can do the comparison. So if I would have gone back to the previous slide, instead of doing log n comparisons per bin, we do just one comparison per bin, so the number goes down to log n. The question is how to implement this OPPRF, programmable pseudo-random function. Apparently, it's not hard. So let's implement it. So suppose we have the OPRF as a black box. People know how to implement it. So Alice says, okay, I want to program this value. And unfortunately, for my xi, I want the output to be this. Unfortunately, the function that I couldn't control gives this value, this output to Bob. And if I give Bob this fixing parameter, which is the XOR of the actual output with the output I want to give, and if he XORs this value to the value that he got from the function, then he'll get this as the output. So basically, Alice goes and for the log n values she cares about, she sees exactly how Bob should fix his input. Now she cannot tell Bob, if you get xi, then fix it with this, because then Bob will know exactly where she wants him to change the function, what she wants to program. Do we want to keep it secret? So instead, what Alice is doing, she knows that for certain xi, she needs to have this, parameter fixing values. So she interpolates a polynomial that for these inputs that she wants to fix, he'll give exactly the values that need to be added to the output of the pseudo-random function to get y star, like the fixing values. So she interpolates its polynomial and sends it to Bob. The nice thing is Alice wants to hide from Bob which x's she wants to fix. So she uses this x's to interpolate a polynomial, and these values look random to Bob because it doesn't know x. And Bob, if I get a polynomial from Alice, I don't know which x's she used to interpolate him. So by sending the polynomial, Bob doesn't know, what were the x's that were used for the interpolation. So what Bob is doing, he evaluates the original pseudo-random function, get the output, and then XOR it with the value of the polynomial applied to his input. And then if his input was one of the values that Alice programmed, then what he get as the output he got here XORed with what she programmed into the polynomial, which is this value, which then the value of f cancels out, and he gets y star. And if his value is not one of the values she programmed, then basically he gets there something random. Okay? So this, she just interpolates a polynomial, sends it to him. The length of the polynomial is the number of items she wants to program. And then he doesn't know which values she wants to set in the pseudo-random function, but he'll get the right result. So she can do it, programs log n items per bin, and then they do just one comparison afterwards in the circuit. The problem is if she has to send a polynomial of length log n per bin, then the total communication will be n log n total. We fix this by seeing that overall, if we're looking at all bins, she only has n items, so she only wants to program n values over the entire polynomial, over all the bins together. So instead of sending n polynomials of degree log n, she can send one polynomial of degree n that will fix all values. So now the communication will be only order of n. So we don't have to program in the padded values. So this is what we did. Okay, and this brings the problem of, okay, we have to interpolate a polynomial over n points, and n is a million, which is, this becomes challenging, and we could use Lagrange interpolations, which runs in quadratic time, and it's quite challenging. And then we used FFT, not over roots of unity, but over arbitrary points. And this has a runtime of n log square n. Actually, it was hard to find the implementation, so we implemented it. And it's actually pretty efficient. Other people have used it as well. Let me also publicize another paper I have where the main author is Alin Tomescu, who is a graduate, and he graduated from MIT. And then we use this technique with FFT. So basically for all threshold signature schemes, it's my time, but I'm okay. I thought I'd have to, I thought I'll be too fast, but okay. So in the other paper, we use the same techniques for all threshold signature schemes, or all threshold schemes in applied crypto, and show that it's going to be much faster if you use this. And this paper was accepted to Oakland to IEEE Security and Privacy. I mean, it's very nice, implementation and experimentation throughout, all the system that you can think of. Okay, and handling the stash, we can also do it. The thing which is not nice is that the stash has to get negligible overhead. It has to be super linear, and this being super constant. And a naive solution will bring the entire overhead to be super linear just because of the stash, which is annoying because for most items you pay linear work, and just for the few items in the stash you have to pay a super linear time. But we can get over that. Okay, this is how to solve the stash. This is almost the last slide. We ran experiments, say with 1 million items and failure probability of 2 to the minus 40. And so this is the sorting network example. This is a result we had in Eurocrypt 2019. This is Eurocrypt 2019. And we reduce communication by a factor of 10. Everything runs much faster. If we compare it to what Google published they're doing using Diffie-Hellman, then we think that in Elan we run 65 times faster, and they also leak the intersection size. So conclusions. So in general, MPC is good in getting rid of trusted parties. Generic MPC is useful and efficient if the circuit size is small. Set intersection is an example of a problem where we don't have a small circuit, but it seems to be important enough to deserve a solution by itself. And here we had a solution which combines both a specific solution and a circuit. So, okay, so one solution they have is they have different variants, and I'm not expert on what they do. As far as I remember, what they're usually interested in is computing the sum of the revenues, which they do by using Diffie-Hellman to identify who's in it, items which are in the intersection in permuted order. So they don't know that I'm in the intersection, that I bought the ice cream, but they identify items which are in the intersection. And then they use additive homomorphic encryption like Payet to sum up the values. And I think they can do also other things with this. And communication is pretty good, but the fact that they use public key crypto for everything makes it slower. Much more simple to understand, but slower. Okay. Thank you.
Yeah, questions?
So are there any results in the n party setting?
Okay, that's a good question. So actually, most of the research was on two-party. With n-party, there are much fewer results. There's a paper of Vlad Kolesnikov, Mike Rusulek, me, and our students Ni and Naoma Tanya from 2 years ago, much less work. Actually, where it becomes really interesting is, and I don't have a good solution, is if you have n parties and you want to find items which are not in the intersection of all of the n sets, but in T of the n sets. Because then the number of subsets becomes exponential, and I don't know how to do it.
So do you use different techniques for dealing with the n-party case? So for the two-party case, you use OPRF, OPRF.
So what we do for the n parties? So okay, so I tell you about our solution for the n parties when we want to find out the intersection of all n parties. So initially they run one-to-one communication. Basically, they agree on keys in very simple one-to-one communication, so that the sum of, if you have a certain item in a set, you're going to send a certain value, and it's going to look random to me and to the others, and each one of us is going to send that value, and the values are going to sum up to 0 if that item is in the set, or sum up to something special. And then you have to combine these values somehow and know, you sent me 1,000,000 values, and he sent me 1,000,000 values, and 20 people all sent me 1,000,000 values. Now I need to know, and if like one from each set, I choose specific ones from each set, if they sum up to 0, then I know that something is intersection, but I don't want to start going over all combinations of all items from all sets. So you need to do something more to do it.
So the oblivious pseudo-random function that you use, would you consider that as a trusted third party, or would it?
So you could, okay, so the oblivious pseudo, okay, I didn't describe how to do an oblivious pseudo-random function. We can consider it for now as a protocol that does an OPRF for us. And if I have 5 more minutes, I can describe how to do it, how to implement it. What I did describe was how, assuming that you have a protocol for computing a pseudo-random function, I showed how to compute an oblivious programmable pseudo-random function, where Alice can program a few outputs of the pseudo-random function without Bob learning which items she programmed in it. Okay, and just learning how to do an OPRF, it's not a big deal.
Any other question?
In previous slides, you talk about that communication and number of items. Yeah, here. So what is the average size of item, or it doesn't depend?
What is the number of items? 1,000,000 items.
Yeah. So the size.
What is the size of each item?
Yeah.
Okay. So not important. Why it's not important? It's slightly important. If the items are too large, you can always hash them to a smaller range. So, I mean, if you use a representation of size 2 log n plus something, then you know that if you have a random hash function and you map everything to a representation of size 2 log n plus something, then by the birthday paradox, you know that you're not going to get collisions. So you can always map the items to that length if they're very long. If they're shorter, then they might be shorter than 2 log n, maybe. Then in that case, you don't need to hash them down. So I don't recall exactly in this example, but in the paper we had both for shorter items and for larger ones, but you don't have to consider items which are larger than 2 log n plus your statistical security parameter.
Okay, so yeah, so very depressing talk, and
Thank you. Thanks.